Welcome to this deep dive. Today, we're trying to get a handle on something, well, pretty fundamental about algorithms, the things running behind so much these days. How do we actually know if one algorithm is, well, better than another one? What's the yardstick?
Exactly. We've got some material that really cuts to the chase
Yeah.
on assessing algorithm efficiency. Our goal here is to uh, clarify the main ways we figure out if an algorithm is good, fast, doesn't hog resources.
hmm
We'll look at two main ways, actually running them to see what happens, and a more conceptual way of estimating performance.
Okay, let's start with that first one, then actual testing. Seems logical, doesn't it? Like, you have a problem, two algorithms that could solve it, so you just run them both, see which one finishes first, or uses less memory, get some real numbers.
That's definitely the intuitive appeal, yeah,
Yeah.
because of those concrete figures, runtime, memory usage in that specific test. But, and this is a big but, relying just on that has some pretty significant drawbacks, as our sources point out.
Hmm. Like, what are the problems with just, timing it on your computer?
Well, first off, the machine you run it on makes a huge difference. I mean, think about it. An algorithm built for parallel processing, it'll probably scream on a multi-core processor. But on an old single-core machine, it might just crawl
Ah, okay.
and flip that maybe an algorithm needs loads of memory. Give it tons of fast RAM, it works great. Try running it where memory is tight, and it might just fall over.
So the hardware you happen to have can totally skew the results. The same algorithm could look amazing on one setup and terrible on another.
Precisely. Which makes it really, really hard to say anything objective or universal about it. And just imagine trying to test across all sorts of different hardware, run
Yeah.
it here, run it there, average it all out, becomes a massive headache pretty fast. Who actually has the resources or the time for that kind of thing?
Right, probably not your average person just trying to pick the best tool for the job. But okay, let's say you could control the hardware, like use the exact same machine every time. Are there still issues?
Oh, absolutely. Because the other big factor is the data you feed it, the size of the input data. You might find algorithm A is super speedy with, say, 10 items, but feed both A and B a million items, and suddenly algorithm B might be way faster. It scales better. So to really understand how they compare, you'd have to test them not just once, but with small data, medium data, large data, huge data. Think about processing orders you'd need to test with 10 orders, 100, 1,000, a million maybe. That takes a ton of time and computing power.
So running tests gives you a snapshot, yeah, but only for that specific machine and that specific data size. It sounds like it's not great for predicting how it'll handle like really big tasks or different setups. So what about that other way, the more theoretical approach you mentioned?
Right, that's where theoretical estimation comes in, often called complexity analysis or asymptotic analysis. Basically, instead of running the code, we analyze it mathematically. We focus on how its need for resources, time, and also memory space changes as the amount of input data gets bigger.
Okay, so less stopwatch, more. Looking at the underlying structure, understanding the relationship between data size and resource use.
Exactly that. It's all about the trend. How does the runtime grow? How does memory usage grow? Think of it maybe like comparing two types of plants. One might be taller right now, but if the other one has a fundamentally faster growth rate, you know it's eventually going to overtake the first one, right?
Ah, I like that. Focusing on the growth rate, not just today's height.
Yeah. Complexity analysis looks at that underlying growth rate.
So how does this theoretical approach get around the problems we saw with actual testing?
Well, the biggest thing is you don't need to run any code
Hmm.
at all. So forget about the hardware. Doesn't matter. Operating system. Doesn't matter either. It's purely analysis.
Okay. Environment independent.
Totally. Which also means it uses way fewer resources. No long test runs needed.
Hmm.
And crucially, it lets us predict how things might behave with different amounts of data, especially those really, really large data sets that can just cripple inefficient algorithms.
So it gives us a way to predict performance before we even start coding or running things. And those predictions hold up across different machines and data scales. That sounds incredibly useful.
It really is. Complexity analysis gives us a kind of universal ruler, you could say, a way to compare algorithms based on how their time and space needs scale up. It helps us spot the ones that are fundamentally built to be efficient as the job gets bigger.
It definitely sounds like this complexity analysis, even if it feels a bit more abstract maybe, is the more reliable way to really understand long-term efficiency.
It can seem abstract at first, yeah, because it is based on math. You'll hear terms like big O notation, which is part of this whole framework. But the core idea really is understanding that growth trend. And honestly, getting even a basic grasp of complexity analysis early on, it's super valuable. It teaches you to think about efficiency right from the start, even with simple stuff. It gives you a way to judge why one approach might just be fundamentally better down the line, no matter what computer you run it on.
Okay, so let's recap. We've looked at two main ways to figure out how efficient an algorithm is. There's the direct approach. Run it, time it, measure it. Actual testing gives you real numbers for one specific situation, but struggles with different hardware, different data sizes. It's limited.
Right. Very context dependent.
And then there's the theoretical estimation, the complexity analysis, more abstract, focused on math, but it looks at the fundamental growth trend, how resource needs scale up with data size.
Exactly. And that makes it much better for predicting performance across different environments and especially with large amounts of data.
Understanding these two methods really seems key then for anyone building or choosing algorithms, especially if they expect them to handle serious workloads.
Absolutely. It's foundational knowledge, really.
This has been really insightful. Thanks. It clears things up a lot. So, thinking about these two approaches, what do you think is ultimately more crucial for predicting how an algorithm will actually perform in the real world, especially when you're dealing with truly massive data sets? And, why is that method maybe more telling in those big data scenarios? Definitely something to chew on. Thanks for this deep dive.